Welcome to this coding walkthrough. In today's session, we're tackling an exciting problem from LeetCode, problem number 253, Meeting Rooms 2. We'll explore how to determine the minimum number of conference rooms required to schedule all given meetings. Let's dive into the details and work through an efficient solution. In this problem, we're given an array of intervals, where each interval represents a meeting with a start time and an end time. The task is to determine the minimum number of conference rooms needed to accommodate all the meetings without any overlapping. The input is a list of intervals, where each interval consists of two integers, the start time and the end time of a meeting. The output will be a single integer, which represents the minimum number of rooms required. For example, if we have overlapping meetings, we'll need more than one room to ensure that no two meetings occur in the same room at the same time. Let's take a look at an example. Suppose the input is intervals equal to 0, 30, 5, 10, 15, 20. The output is 2. Here's why: the first meeting spans from 0 to 30, overlapping with the second meeting, which runs from 5 to 10, and the third meeting, which runs from 15 to 20. To accommodate this setup, we need two rooms. Room 1 handles the first meeting from 0 to 30, while Room 2 is used for the second meeting from 5 to 10 and then the third meeting from 15 to 20. As their times don't overlap. This ensures that all meetings are scheduled without conflicts. Here's another example. If the intervals are 7, 10, 2, 4, the output is 1. This is because the two meetings do not overlap in time. The first meeting ends at 4, and the second meeting doesn't start until 7, so both can be accommodated in the same room. Now consider a more complex case with intervals 1, 5, 2, 6, 3, 8, 10, 15. The output is 3. Meetings 1, 2, and 3 overlap, so we need 3 different rooms for them. Room 1 handles the first meeting from 1 to 5, Room 2 handles the second meeting from 2 to 6, and Room 3 handles the third meeting from 3 to 8. Once these meetings conclude, the fourth meeting, from 10 to 15, can be scheduled in any of the now available rooms. Finally, let's review the constraints and edge cases. The number of intervals can range from 1 to 10,000, and the meeting times are between 0 and 1 million. Importantly, the intervals may not be sorted, so the solution must account for this. For edge cases, if there's only one meeting, only one room is needed. For non-overlapping meetings, a single room is sufficient as well. However, if all meetings overlap, the number of rooms required will equal the total number of meetings. For example, with intervals 1, 10, 2, 9, 3, 8, 4, 7, where every meeting overlaps, we would need 4 rooms. Additionally, the solution must handle unsorted input, such as 7, 10, 2, 4, 5, 8, which still requires careful scheduling to determine the correct number of rooms. In this problem, we need to determine the minimum number of conference rooms required to host all given meetings, where each meeting is defined by a start and end time. The key challenge here is handling overlapping meetings, as each overlap necessitates a separate room. We first consider a brute force approach. The idea is simple: for each meeting, we check how many other meetings overlap with it. This involves using nested loops to compare each interval with every other interval, counting overlaps, and then determining the maximum number of simultaneous overlaps. While this method is straightforward to implement and requires no additional data structures, it quickly becomes inefficient for larger inputs due to its n² time complexity. This makes it unsuitable for scenarios where scalability is a concern. Instead, we explore a more efficient approach using a min-heap, which we'll now discuss. The min-heap approach offers a more optimized way to handle this problem. Instead of explicitly checking overlaps, we use a priority queue to track the earliest end time of ongoing meetings. Here's the process. First, for each meeting, we remove rooms from the heap if their end times are less than or equal to the current meeting's start time. This step reflects that those meetings have finished and their rooms are now available. Then, we add the current meeting's end time to the heap to indicate that a room is occupied. The size of the heap at any given moment represents the number of rooms currently in use. To implement this, we start by sorting the intervals by their start times. As we iterate through these intervals, we update the heap dynamically. This approach combines the efficiency of sorting with the dynamic management of a heap, yielding a time complexity of O(n log n) due to sorting and heap operations. the space complexity is O(n) to store the heap. This method is particularly well suited for interval-based problems and ensures scalability. An alternative to the heap-based method is to use two separate arrays to manage the start and end times of meetings. The intuition here is to split the intervals into two parts, one array for start times and another for end times. By sorting these arrays and iterating through them using two pointers, we can track the number of ongoing meetings. For each start time without a corresponding end, we increment the room count, and for each end time, we decrement it. This approach effectively tracks room usage without the need for a heap. The implementation involves sorting the start and end arrays and then using the two-pointer technique to iterate through them. This results in a time complexity of O(n) log n due to sorting, with a space complexity of O(n) for the arrays. While this method is slightly easier to implement than the heap-based approach, dynamically managing ongoing meetings is less intuitive. It's a solid alternative, but the heap offers greater flexibility for similar problems. The heap-based approach was ultimately chosen as the preferred strategy for solving this problem. This method provides a clean and efficient way to manage overlapping meetings dynamically. By sorting the intervals, we ensure that the meetings are processed in chronological order, and the heap allows us to keep track of the earliest end times efficiently. This combination directly models the problem's requirements and minimizes unnecessary computations. While the two-pointer approach is a viable alternative, the heap-based method is more generalizable and can be applied to a broader range of interval-based problems. One key insight in this approach is that the number of overlapping intervals determines the number of rooms required. Tracking the earliest end time is crucial for minimizing the number of rooms in use, and the heap offers an optimal way to do so. This realization simplifies the problem and provides a structured solution to what initially appears to be a complex task. When comparing the different approaches, there are clear trade-offs to consider. The heap-based approach and the two-pointer method both share a time complexity of O(n) log n. However, the heap is more versatile for managing dynamic interval problems, making it a better long-term choice for similar scenarios. On the other hand, the brute force method, while easy to understand, is impractical for larger inputs due to its O(n)² time complexity, which makes it inefficient for scaling. In conclusion, the heap-based approach strikes a balance between efficiency, clarity, and scalability. It leverages sorting and dynamic management effectively, providing an optimal solution to the problem while remaining flexible enough to handle variations of interval-based challenges. The problem we are tackling is to determine the minimum number of conference rooms needed to schedule all meetings without any overlap. If two meetings overlap in time, they will require separate rooms. Each meeting is represented as an interval with a start and end time, such as start-end. To solve this efficiently, we use a greedy algorithm combined with the two-pointer technique. First, we parse the input, which is a list of intervals representing the meetings. We extract the start times and end times into two separate lists. Then, we sort these lists in ascending order. Sorting the start and end times ensures that we can process the meetings in the order they occur, which is crucial for efficiently allocating rooms while minimizing unnecessary computations. Now, we proceed with the two-pointer technique. We use two pointers, I to track the current meeting being started, and J to track the earliest meeting that has ended. We also initialize two counters, rooms_needed, which keeps track of the current number of rooms required, and max_rooms, which records the peak number of rooms needed at any point. As we iterate through the start times, if the current meeting's start time is earlier than the earliest meeting's end time, it means the meetings overlap, and we allocate a new room by incrementing rooms_needed. We then update max_rooms to reflect the highest value of rooms_needed. On the other hand, if the current meeting starts after or when the earliest meeting ends, we free up a room by moving the J pointer forward and decrementing rooms_needed. This process continues until all meetings have been processed, and the value of max_rooms at the end gives us the minimum number of conference rooms required. There are several key insights that make this approach efficient. First, sorting the start and end times is essential. By processing meetings in chronological order, we avoid unnecessary backtracking or repeatedly comparing overlapping intervals. Second, the two-pointer technique allows us to efficiently track which meetings are ongoing and when rooms can be freed. This eliminates the need for a nested comparison of every meeting with every other meeting, which would otherwise result in O(n)² complexity. Finally, dynamically maintaining rooms_needed and updating max_rooms ensures that we always have an accurate count of the rooms required at any point in time. The use of separate start and end arrays, which are sorted, along with these counters, provides a streamlined way to handle room allocation in real time as we process the meetings. Let's analyze the time and space complexity of our approach. Sorting the start and end arrays is the most computationally expensive step, taking n log n time, where n is the number of meetings. Once sorted, the two-pointer iteration only requires a single pass through the start and end arrays, which takes n time. For space complexity, we need n space to store the start and end arrays. Therefore, the overall time complexity of the algorithm is n log n, and the space complexity is n. To illustrate this, consider the example input 0, 30, 5, 10, 15, 20. After extracting and sorting the times, the start array becomes 0, 5, 15, and the end array becomes 10, 20, 30. These sorted arrays set the stage for efficient processing of the meetings. Using the sorted start and end arrays, we can now apply the two-pointer technique. At the beginning, both pointers I and j are at position 0. The first meeting starts at time 0, which is before the earliest meeting ends at time 10. We allocate a room, so rooms_needed becomes 1, and max_rooms is updated to 1. At the next start time, 5, the meeting still overlaps with the one ending at 10, so we allocate another room, bringing rooms_needed to 2, and updating max_rooms to 2. When we reach the third meeting, starting at 15, it begins after the first meeting has ended. This allows us to free one room by moving j to the next end time, decrementing rooms_needed to 1. However, since a new meeting is starting, we allocate a room again, bringing rooms_needed back to 2. At the end of the iteration, the maximum number of rooms needed at any point was 2, which is our result. Thus, the minimum number of conference rooms required for this input is 2. This code solves the LeetCode problem meeting rooms 2 using a greedy approach combined with a min-heap, or priority queue. The objective is to determine the minimum number of meeting rooms required to schedule all given intervals of meetings. First, we check if the input intervals is empty. If there are no meetings, no rooms are needed, so we return 0 immediately. Next, we sort the intervals based on their start times using the sort method with a lambda function as the key. Sorting ensures we process meetings in chronological order of their start times. We use a min-heap to efficiently track the end times of ongoing meetings. The heap will always contain the end times of meetings currently occupying rooms. Initially, we add the end time of the first meeting to the heap. Then, we iterate through the remaining intervals. For each meeting, we check if the earliest ending meeting, the root of the heap, has already finished before the current meeting starts. If so, we remove it from the heap using heap.heappop, freeing up a room for the current meeting. Whether a room is freed or not, we add the current meeting's end time to the heap using heap.heappush. This ensures that the heap always reflects the end times of ongoing meetings. At the end of the loop, the size of the heap represents the maximum number of rooms required at any point, which is our result. This approach is efficient, with a time complexity of n log n due to the sorting step and heap operations, and a space complexity of n for the heap. This solution handles all edge cases, including empty input, overlapping meetings, and cases where all meetings overlap. It ensures correctness and efficiency for large inputs. Here, we begin by importing the required classes and defining the solution class with the min-meeting_rooms method. The goal of this method is to determine the minimum number of meeting rooms required for a given set of intervals. First, we handle the edge case where no intervals are provided. If the intervals array is null or empty, we simply return 0 because no meetings mean no rooms are needed. Next, we sort the intervals by their start times to process the meetings in chronological order. This ensures that we always evaluate meetings in the correct sequence. After sorting, we create a priority queue, implemented as a min-heap, to keep track of the earliest ending meeting at any given time. Priority queues are useful here because they allow us to efficiently manage meeting end times as new meetings are scheduled. We start by adding the end time of the first meeting to the heap, since it will always occupy a room. Then, we proceed to iterate through the remaining intervals. For each interval, we check if the current meeting can reuse a room by comparing its start time to the earliest ending meeting in the heap. If the current meeting starts after or at the same time as the earliest ending meeting, we remove that meeting from the heap, effectively reusing the room. If the current meeting cannot reuse an existing room, we simply add its end time to the heap, indicating a new room is needed. This process ensures that the heap always contains the end times of the meetings currently in progress. Once all intervals have been processed, the size of the heap represents the number of meeting rooms required, as each entry in the heap corresponds to an ongoing meeting at a specific time. Finally, we return the heap size as the result. This implementation is efficient because sorting the intervals takes O and log n, and each heap operation is logarithmic, making the overall time complexity O n log n, where n is the number of intervals. This ensures that the solution is both optimal and scalable for larger inputs. Here, we start with a basic example to understand the problem. The input intervals represent meeting times, and we need to determine the minimum number of meeting rooms required. First, we initialize the state with the given intervals 0, 30, 5, 10, 15, 20. Next, we sort these intervals by their start times to process them in chronological order, which doesn't change the order in this case. We then initialize a min heap with the end time of the first interval, which is 30. The heap helps us keep track of the end times of ongoing meetings. Now, when we process the second interval, 5, 10, we check if the room with the earliest end time, 30, is free. Since the start time 5 is less than 30, a new room is allocated, and we add the end time 10 to the heap. At this point, the heap has two values, 10, 30, indicating two ongoing meetings. Next, we process the third interval, 15, 20. We again check if the room with the earliest end time, which is now 10, is free. Since the start time 15 is greater than or equal to 10, it means the previous meeting in that room has ended, and we can reuse the room. We remove 10 from the heap and add the end time 20 of the current interval. The heap now contains 20, 30, representing the ongoing meetings. Finally, the size of the heap at the end of processing all intervals is 2, which means we need a minimum of 2 meeting rooms. Moving to a new example, we now consider overlapping meetings. For the input intervals 7, 10, 2, 4, we first initialize the state and then sort the intervals by their start times. After sorting, the intervals become 2, 4, 7, 10, allowing us to process them in chronological order. To begin processing, we initialize the min heap with the end time of the first interval, which is 4. The heap now contains 4. Next, we process the second interval, 7, 10. We check if the room with the earliest end time, 4, is free. Since the start time 7 is greater than or equal to 4, the previous meeting has ended, and we can reuse the room. We remove 4 from the heap and add the end time 10 of the current interval. The heap now contains 10, representing the ongoing meeting. At the end of processing all intervals, the heap size is 1, which means we only need 1 meeting room. This example illustrates how the min heap efficiently helps us track and allocate meeting rooms based on room availability. Now, let's explore a case where all the meetings overlap. In this example, the input intervals are 1, 5, 2, 6, 3, 7. First, we initialize the state with these intervals, and then we sort them by start times, which doesn't change their order here. After sorting, we initialize the min heap with the end time of the first interval, which is 5. The heap now contains 5, indicating one ongoing meeting. Next, we process the second interval, 2, 6. We check if the room with the earliest end time, 5, is free. Since the start time 2 is less than 5, the room is not available, so we allocate a new room. We add the end time 6 of the current interval to the heap, which now contains 5, 6, representing 2 ongoing meetings. This demonstrates how the heap grows when overlapping meetings require additional rooms. Now, we process the third interval, 3, 7. We again check if the room with the earliest end time, 5, is free. Since the start time 3 is less than 5, the room is still occupied, so we allocate another new room. We add the end time 7 of the current interval to the heap. The heap now contains 5, 6, 7, representing 3 ongoing meetings. At the end of processing all intervals, the size of the heap is 3, which means we need a minimum of 3 meeting rooms. From these examples, we can derive key insights. The min heap tracks the n times of ongoing meetings, and the smallest value in the heap represents the earliest room that becomes free. Sorting intervals by start time ensures we process meetings in chronological order. If a new meeting starts after a room becomes free, we reuse the room by removing the earliest end time from the heap. The final size of the heap gives us the minimum number of rooms required. To analyze the time complexity of our solution, let's break it down into its main components. First, sorting the intervals by their start times using the intervals.sort operation takes O and log n, where n is the number of intervals. Sorting dominates this step because we are arranging the intervals in chronological order, which is essential for processing them efficiently. Next, we handle the intervals using a min heap to track meeting n times. For each of the n intervals, we perform 2 key operations on the heap: insertion and removal. Insertion, handled by heap.heapPush, and removal, handled by heap.heapPop, both take O log k time, where k is the size of the heap. In the worst case, when all meetings overlap, k can grow to n, making each operation take up to O log n. Since we perform these operations for all n intervals, the total time spent on heap operations is O n log n. Combined with the sorting step, the overall time complexity becomes O n log n. Now that we've analyzed the individual components, the total time complexity of the solution can be summarized as O n log n. This comes from the sorting step and the cumulative heap operations, both of which scale similarly. Let's move on to the space complexity. The primary space usage comes from the heap, which stores the n times of the meetings currently in progress. In the worst case, where every meeting overlaps, the heap may need to store all n intervals, resulting in O n space usage. As for the input list, it is sorted in place. This means no additional space is required for sorting, and the input storage does not contribute to the overall space complexity. Thus, the total space complexity is dominated by the heap and is O n. The overall space complexity can be summarized as O n, driven entirely by the heap, which stores the n times of overlapping meetings. Sorting the input list does not require extra memory beyond the original list, as it is performed in place. To put this into perspective, let's compare our optimized approach to a brute force method. In a naive solution, we would compare each meeting with every other meeting to check for overlaps, which would take O n squared time for n intervals. Additionally, storing overlap information would require O n space. By contrast, our current solution, with its use of sorting in a heap, reduces the time complexity to O n log n, while maintaining the space complexity at O n. This demonstrates how the optimized approach is much more efficient at handling the problem. Let's consider the best, average, and worst case scenarios for our solution. In the best case, where no meetings overlap, the heap size remains at 1 throughout the process. Even though heap operations are minimal in this scenario, the time complexity is still dominated by the sorting step and remains O n log en. For the average case, where meetings overlap to some extent, the heap grows moderately to accommodate overlapping intervals, but the time complexity remains O n log n, due to the sorting step dominating. Finally, in the worst case, when all meetings overlap, the heap grows to its maximum size of n. Even in this scenario, the time complexity remains O n log n, and the space complexity is O n, because the heap must store all n meeting n times. These cases highlight how our solution handles different input scenarios efficiently. Let's solidify our understanding with a mathematical proof for the big O complexity. Sorting the intervals dominates the time complexity, taking O n log n. The heap operations scale logarithmically with the number of meeting rooms, O log n, and since these operations are performed for all n intervals, they contribute O n log n in total. Combining these, the overall time complexity is O n log n. As for the space complexity, the heap is the primary contributor, as it grows to O n in the worst case when all intervals overlap. Therefore, the final space complexity is O n. These combined factors confirm that our approach is both time and space efficient, making it well suited for solving this problem in practice. When solving meeting rooms too, there are some common mistakes that can lead to incorrect results or inefficiencies. A key issue is failing to sort both the start and end times. Many assume sorting just the start times is enough, but this approach does not account for the proper sequencing of when rooms become available. Both start and end times must be sorted separately to ensure accurate tracking of overlapping meetings. Another mistake involves using nested loops to check overlaps. This brute force method has a time complexity of n squared, which becomes highly inefficient for larger datasets, like when the number of meetings exceeds 10,000. Additionally, overlooking edge cases can cause significant problems. For instance, scenarios like having 0 meetings, only 1 meeting, or meetings with identical start and end times must be handled explicitly to avoid runtime errors or incorrect outputs. Lastly, some developers struggle with managing the min heap correctly. If you forget to update the heap when a meeting ends, it can lead to overallocation of rooms, as the algorithm no longer reflects the true state of availability. Another common mistake is mismanaging time intervals, particularly assuming that meetings with the same start and end time don't require a room. This is incorrect because even in such cases, a room must be allocated to accommodate the meeting, however brief it is. Now, when it comes to interviews, there are several insights to keep in mind. A major focus is the sweepline approach, which involves sorting both start and end times and efficiently tracking overlapping intervals. This method allows you to reduce the problem to managing room allocation dynamically. Using a min heap to track end times is an excellent optimization because it ensures that the smallest end time is always accessible, resulting in an overall time complexity of n log n. It's also crucial to clarify edge cases during the interview, such as how to handle negative times, overlapping intervals, or meetings starting and ending simultaneously. Additionally, be prepared to discuss time complexity trade-offs, such as why sorting-based approaches are more optimal than nested loops. Finally, if prompted, you can mention alternative methods like the two-pointer technique, though the heap-based solution is generally preferred for this problem. This problem has connections to several related problems on LeetCode that you might find helpful to study. For instance, LeetCode 56, Merge Intervals, challenges you to merge overlapping intervals, which shares similarities in terms of sorting and interval management. LeetCode 252, Meeting Rooms, focuses on determining whether all meetings can be attended without conflicts, which is a simpler version of this problem. Of course, LeetCode 253 is the current problem we're solving, Meeting Rooms 2. Other related problems include LeetCode 759, Employee Free Time, which involves finding gaps in schedules, and LeetCode 1229, Meeting Scheduler, which explores finding overlapping time slots for multiple individuals. Additionally, there are alternative approaches to solving this problem, each with its own trade-offs. The two-pointer technique is one such approach. By using 2 pointers to traverse the sorted start and end times, it achieves a similar result to the heap-based method but may be slightly faster in practice. However, some find it less intuitive compared to the heap-based solution. Another option is using an interval tree, which allows for dynamic updates to intervals. While powerful, this approach is more complex to implement and may not be necessary for this problem. Lastly, there's the brute force approach, where you compare every pair of intervals to check for overlaps. While this method is conceptually simple, it's highly inefficient with a time complexity of n squared. This makes it suitable only for small input sizes, as it quickly becomes impractical for larger datasets. While brute force might help you understand the problem initially, it's not a viable solution for real-world scenarios or competitive programming. Instead, it's important to focus on more optimized techniques like the min-heap or two-pointer approaches, which are better suited for handling large-scale inputs efficiently. Great job following along. To recap, we used a greedy approach with sorting and a min-heap to solve the Meeting Rooms 2 problem efficiently. This method is not only optimal for this problem but also widely applicable to similar challenges involving intervals and resource allocation. Thanks for joining me, and don't forget to like, share, and subscribe for more tutorials. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!